Hello, fellow physicists. Welcome back to Naomi Nye, the Science Guy. Today we're at the hub of rides and roller coasters, Universal Studios. I'm your host, Naomi, and I'm joined by our special guest, Dowie. How are you feeling today?
I'm feeling very excited to learn about the physics of roller coasters.
I'm very glad to hear that. Let's get started. Roller coasters are devices that are powered by kinetic and potential energy. While many think of the many thrills and stomach-dropping feeling as they ride down, there's actually quite a lot behind roller coasters and their logistics. Roller coasters use multiple areas of physics, from energy to inertia and gravity, to keep their rides going.
In an ideal closed system, the total energy of a system should be potential energy plus kinetic energy equals total energy. However, within these idealized systems, we often assumed that the energy is 100% conserved. But that is not always true. In a real-world scenario, energy is lost due to wind resistance, heat, sound, and friction.
Time for our favorite part of this physics video, that is derivation. Let's start with a derivation for velocity when friction is negligible. Assuming the system consists of the cart and the earth, at the maximum point of the track, which we labeled as h0, the system only contains gravitational potential energy, which is mass times acceleration due to gravity times height. As the cart travels down the track, its gravitational potential energy is being transformed into kinetic energy. Here we begin our derivation using the conservation of energy equation. Energy initial equals energy final. The starting gravitational potential energy should equal to the final kinetic energy. Plugging in corresponding equations, mgh0 equals 1/2 mv squared. And in the end, we derive that the velocity equals square root of 2gh0. Now considering that friction is non-negligible. As the cart accelerates down the track, there is an opposing force of friction that points up the track. We labeled the distance d, the height h0, and drew the free body diagram with force components. Friction does work on the system. Starting with the equation energy initial plus work equals energy final, we can plug in corresponding variables, simplifying the equations, and achieve the final derivation, that is v equals square root of 2g times h0 minus mu cosine theta d, where theta is the angle between the track and the horizontal baseline, and mu is the friction coefficient. As we can see, energy is lost when friction is non-negligible. The velocity achieved with no friction is greater than the velocity achieved with friction, which means the kinetic energy is less in this case. Next, onto our derivation for g-force. G-force, or gravitational force, is a measurement of acceleration caused by gravity. It is also known as mass-specific force and is expressed in units of standard gravity. G-force is used to describe sustained accelerations that cause weight perception. For example, an object at rest on Earth's surface is subject to 1g, which is a conventional value of gravitational acceleration on Earth, about 9.8 meters per second squared. Roller coasters rely on this force to cause funny feelings in our bodies. When you plummet down a steep hill, gravity pulls you down while the acceleration force seems to pull you up. At a certain rate of acceleration, these opposite forces balance each other out, making you feel a sensation of weightlessness, the same sensation a skydiver feels in freefall. Assuming the cart is entering a perfectly circular loop, we start with the equation net force equals mass times centripetal acceleration. The net centripetal force is caused by the normal force minus the perpendicular component of Fg. G-force in this case is a ratio between normal force and mg. So here we're plugging in what we already derived for normal force in the center of the screen. Since we're calculating the g-force of an instant when the car is in the loop, the car's velocity equals 2gh0 minus h. To further simplify the derivation, we drew the loop again and labeled the radius, and we derived that h equals r times 1 minus cosine theta. And now we are rewriting the derivation and plugging in r times 1 minus cosine theta for h. Then we are further simplifying, and this is where you should pay attention to your order of operation and where you should FOIL and where you should not, because this took us more than 30 minutes to figure out. And here we're using a previous derivation for velocity, where when the car first enters the loop, its velocity equals square root of 2g h naught. And simplifying, we get h naught equals v naught squared over 2g. Plugging in v naught squared over 2g for h naught, we arrive at the final derivation that is g equals v naught squared over gr minus 2 plus 3 times cosine theta. Just when you thought we were done, now we're estimating the velocity of the Hulk ride. Now there are a lot of assumptions that we had to make and some guesses on the measurements, but here we're using and applying our physics concepts, and that's all that matters. And here's our friend v equals square root of 2gh again, and now we're just plugging in the measurements that we found online. In the end, we estimated that the velocity of the ride is 25 meters per second or 55.9 miles per hour. And according to Google, the actual speed of the ride is 67 miles per hour. And that is it for this video. Thank you for watching, and I hope you learned a lot about the physics of roller coaster today. I don't think I will see you next time, so bye.